Hello, everyone. Can you hear me?
Yes, you're audible, Mesh.
Thank you. We'll just wait for some more time in case there are other participants who are planning to join.
Hi, Greta. Where is my Zoom? Look, and leave again.
We'll just wait until 10:15. If nobody joins till then we'll just get started at 10:15. Yeah. Thank you. Hi, everybody. Can you hear me?
Yes, Umesh, you're audible.
Thank you. Thanks a lot. So let's get started. Thank you, those who have joined us today for this session on conservation biology. That's starting off today's the last day's sessions in Inclusive Ecology 2023. We don't have too many participants joining us today, so we can make this slightly more informal and more of a discussion than sort of a more formal workshop kind of thing. So I just want to ask people what do you think when you hear the term conservation biology? What does it mean? What does it mean to you? If you like, you can type in the chat box. But when you hear, I'm sure a lot of people have heard the term conservation biology, right? I mean, when you hear that term, what does it mean? What do you think conservation biology is?
Protecting the species of interest.
Hmm? Yeah. Anyone else?
Umesh, we do have an answer in chat box also.
Oh, I see. Hang on a minute. Let me just take a look at the chat box. Whoa, why can't I find the chat box? Ah, here it is. Strategies to, I should say strategies to protect flora and fauna. Yes, that is part of conservation biology. But do you think conservation biology is right? Lachutam is saying it's using science-based data to direct conservation efforts, right? Do you think conservation biology is more about the science of conservation or more about the practice of conservation? So is it more about studying habitats and species and ecosystems, or is it more about doing something, making interventions to conserve species, habitats, and ecosystems? More of practice, right? So you're right in that conservation biology has been moving towards more of practice and trying to incorporate science in the practice of conservation. But when the field of conservation biology started, excuse me, it was trying to use concepts in ecology to try and understand how ecosystems, how species, how habitats are responding to the kinds of impacts that human beings are causing on natural systems. And then once we know what those impacts are, to try and use that information now to put this into practice, to put this into operation to try and protect these species and these habitats. Uh, but this particular session is not more about conservation biology as a whole, but more about the kinds of studies that go into the field of conservation biology, the kinds of studies that we can do in conservation biology. It's not going to focus on the practice of conservation because the practice of conservation is very, very complex. That depends on, economics, sociology, politics, a whole lot of, cultural implications of conservation interventions and so on. So actual conservation on the ground is a very complex enterprise, of which science or using science is one part. So today what we're going to look at is the kind of studies that conservation biologists do on the science part of conservation, because conservation biology from one side to the other, the practice of conservation from one side to the other will be very, very different because each site is different in terms of its local cultural context, politics, economics, and so on and so forth. Let me start off by asking, do people know how many mass extinctions there have been on Earth? Life on Earth is 3.8 billion years old, and there have been a certain number of mass extinctions. Does anybody know how many mass extinctions have been there? 6. Vikas says 6. Ashwini says 5. Anyone else? Saravanan says 5. Madhur says 5. What is a mass extinction? Let me define this. Speciation is the process by which new species are formed. The opposite of that is extinction, where a species completely disappears from Earth, right? Now, there is a background rate of speciation and extinction on Earth naturally. Over time, species come into being through speciation, and over time, certain species are lost because of extinction, and there is a certain rate at which that happens. A mass extinction is when that rate is increased drastically in a very, very short period of time. So that's what a mass extinction is. Most people are saying that there have been 5 mass extinctions. The most famous one, of course, is the extinction of the dinosaurs about 65 million years ago. What could be the causes of these mass extinctions? While people are thinking about that, we are actually, because he says 6 mass extinctions, we are actually living through a mass extinction. We are currently living through the 6th ever mass extinction in the history of life on Earth. So in 3.8 billion years, in the past, there have been 5 mass extinctions. The last one was 65 million years ago, which killed off all the dinosaurs. And now we are living through the 6th mass extinction that's been caused entirely by human beings. So it's a mass extinction being caused by one species, humans, and the impacts that humanity is having on biodiversity. But what has really led to mass extinctions in the past? What killed the dinosaur? Asteroid hits, kills the dinosaurs. What else? What else could cause a mass extinction? Natural disasters, natural fact. No,
Climate change.
Climate change, yes, like climate change is today causing a mass, contributing towards a mass extinction. And yeah, okay, natural disasters, natural factors. Can you think of a natural phenomenon that could be classified as a natural disaster? Some volcanic eruption, exactly, right? So volcanic eruptions are something that can be catastrophic and have led to mass extinctions in the past. Global changes, the ever-evolving Earth, absolutely right. Climate either cools or warms even normally. And when the rate of cooling or warming is very, very fast, we see a lot of species being unable to adapt to those sudden changes in the Earth's atmosphere or environment, leading to a large number of species going extinct. So in the past, we've had all of these things: rapid cooling, rapid warming, sudden reductions in the concentration of oxygen in the atmosphere, volcanic eruptions, and so on and so forth, causing mass extinction. Today, like I said, we're living through the 6th ever mass extinction. If you look at the left, what you see is see the dotted line on the left side. Can you see my mouse? Can you see my pointer?
Yes.
Okay. So you see this dotted line here. That is what's called the background rate of extinction, which is the kind of extinction that you would expect even without any catastrophic impacts. Even in the absence of climate change, even in the absence of volcanism, there would be some rate at which species go extinct. And if you have any questions or comments, please do type them into the chat box as we go along. But today, you see that the rate at which species are going extinct is far higher than the background rate of extinction. So, whether it comes to mammals or birds or other vertebrates like reptiles and amphibians, the rate at which species are going extinct is far, far higher today than it ever was, than the background rate of extinction. If you add this all of this comes from data from locations. Sorry, 1 minute. All this comes from information that is there cited at the bottom of the screen there. If you look at the next graphic here, that comes from the World Wildlife Fund's Living Planet report, where if you look at populations of vertebrates, so that includes fish, amphibians, reptiles, birds, and mammals. If you look at the populations of vertebrates in 1970 as the baseline population, right? If that baseline population is scaled to 1, right? So, and then you lose 50% of the population, you'll come down to 0.5, right? We have lost 68%, not of species, but 68% of the populations of vertebrates from 1970 until today. So about 70% of the world's vertebrate populations have reduced in size by 70%. So we're having huge impacts on biodiversity. And that is why it has been proposed that this geological era be called the Anthropocene. Anthropos meaning human, and because we're having these huge impacts, we should call this the age of humans or the Anthropocene. And this is a term that you will hear very often in conservation biology, which is Anthropocene ecology or Anthropocene biology or what's. Look at the way in which we're changing the Earth's environment. On the right side, the amount of plastic that is there on Earth, it outweighs the total biomass of all animals by a factor of 2. So if you take all animals and you add up their body masses, that comes to 4 gigatons of body mass. Plastic is 8 gigatons. So there's twice as much plastic in terms of mass, in terms of weight on the Earth, as there are a total number of weight of the animals on Earth. Very recently, the amount of buildings and infrastructure that we've built, highways, flyovers, buildings, and so on, airports, has overtaken the total biomass of vegetation on the planet. So trees and shrubs account for about 900 gigatons of biomass, whereas our buildings and infrastructure, concrete, cement, and so on, accounts for 1,100 gigatons. So our construction is now outweighing the biomass of vegetation on the Earth. If you look at mammals, a mammal biomass, take all the mammals in the world and add up their body weights. 96% is either humans or their livestock: cows, goats, sheep, chickens. Mammals, cows, goats, sheep, camels, and so on. Right. So 60% of the biomass of mammals on Earth comes from livestock, comes from our domesticated animals. Humans account, there are 8 billion humans on Earth. We account for 36% of the biomass of all mammals on Earth. Only 4% of the biomass today is wild mammals. So even though you do have in the wild, you have large species like elephants and rhinoceros and so on. And blue whales, for example, blue whale is the largest animal that has ever existed on Earth. We and our livestock far outweigh the biomass of wild animals on Earth. We account for 96% of the biomass of mammals on Earth. So, excuse me. So we really are having massive impacts on biodiversity, on the natural world, and that's why it's been proposed that we call this era the Anthropocene. The same thing, not just vertebrates, but invertebrates as well, are showing huge declines. So again, 1970 as a baseline year, if the relative abundance of arthropods is one, of invertebrates is one, then you've seen that there are massive declines until about 2008 in the abundance of arthropods. This is not the number of species, but this is the total number of invertebrates. So if you had, for example, 100 butterflies, just to scale this, 100 butterflies in 1970, then the number of butterflies has now come down to about 40 butterflies in 2008. So we're losing not only species, but also the biomass of these species. The number of species is also reducing because of extinction, but the number of individuals or the population size is also reducing in the wild. And with invertebrates like honeybees and butterflies, the loss of these animals has huge consequences for not only native biodiversity and the wild, but also for human well-being. Because bees, for example, are the greatest pollinators in the wild, as well as on human crops. So today, with the loss of bees, what's happening is that there is now a multi-million-dollar industry that actually transports bees from one plantation to another. You know, like an orange plantation which is flowering, but now there are no bees to pollinate those flowers, right? And so there's no fruit output. And so people are actually moving bees from one in a truck from one plantation to another to take these bees there, pollinate those flowers, and then the bees come back to the truck and then they move on to the next thing. So it does have huge costs even for humans, not only the wild. So there are economic costs from the loss of invertebrates as well as the loss of mammals and other kinds of biodiversity. Again, please do type in questions into the chat box in case you have any questions or in case you want to make any comments or if you would like to elaborate on any of these points. All right, we talked about being in the Anthropocene. We talked about the fact that wild populations are declining drastically in size. We talked about the fact that species are going extinct. Today, what do you think are the causes that species are going extinct? Not in the past, not the past mass extinctions, but today, what are human beings doing that is causing species to go extinct? Habitat destruction? Yes, absolutely. And can you think of the forms that habitat destruction takes? Unsustainable use of natural resources, and another very important cause, which is in the conservation biology literature, is called overharvesting, right? So urbanization is a form of habitat destruction. Pollution, yes. Let's deal with this sequentially. So habitat destruction comes in many forms. One of those is urbanization, like Sri Ganapathy is pointing out, where you lose a habitat and you replace it with urbanized habitat, right? You replace it with cities or you replace it with settlements or villages. You can also have deforestation, like for other purposes, right? You can clear forest so that you replace it with agriculture, for instance. The unsustainable use of natural resources, like I was saying, is called overharvesting. So you're taking out more than can be renewed in the wild. Alien invasions is another very important factor for biodiversity decline. The use of artificial fertilizers, again, contributes to pollution uh, and does have impacts on biodiversity. We're missing one really big change. Land use change, of course, where, you know, habitat loss, deforestation, urbanization, all of them come under land use change. So land use change is, again, in conservation biology literature, you'll find the term land use change being used very, very often. And land use change incorporates under it habitat loss because of deforestation, conversion to agriculture, conversion to cities, and so on and so forth. So land use change is a very broad category of human impacts on the environment. Climate change is now absolutely an absolutely important cause for biodiversity declines. And we will talk about climate change and how we study climate change in conservation biology. Habitat fragmentation is another form of habitat destruction, and we will also look at what habitat fragmentation does to biodiversity. Habitat fragmentation is basically where you have a large patch of natural habitat, but that then becomes fragmented into smaller patches of natural habitat that are then separated by non-natural habitat. So, for example, you could have little patches of forest that are embedded in a larger landscape of tea plantations. So that then you're left with tiny habitat fragments embedded in what's called a matrix that is not suitable for biodiversity. And we look at how we study the impacts of habitat fragmentation as well. Because hunting, yes, for a lot of taxonomic groups, hunting is a huge problem. And that comes under this unsustainable use of resources, because even hunting or fishing, for example, we tend to view fish as a natural resource. In the same way, a lot of people tend to view large mammals, for example, as a natural resource. And so the overharvesting through hunting, overharvesting being where you hunt more than the ecosystem can replace, that again is a big cause for biodiversity declines. We're going to get into all of this, except for invasive species. We're going to talk about this in some detail, except for invasive species. Can you give us examples of invasive species in India that are threatening biodiversity in India? Invasive species. Water hyacinth, absolutely. In aquatic freshwater habitats, water hyacinth just takes over and chokes the surface of the freshwater habitats. Water hyacinth 1. What else? Any other examples of invasive species? Prosopis juliflora, which is called mesquite. It is an arid zone plant that comes from the New World. It comes from Central America and Southern North America, and in dry, arid savanna grasslands, Prosopis has definitely taken over a large part of our grassland biome. Parthidium grass, Parthidium hysteroporus, again is a huge invasive species. Lantana is an invasive. Lantana was brought by the British to India, to the Western Ghats, as an ornamental plant, and the British planted it in their gardens as an ornamental plant because the flowers they thought were pretty, and then lantana has just exploded not only in the Western Ghats but all across India. You will find lantana now. Any other examples of invasive species? Bullfrogs, Nafisa, yes. Not bullfrogs are not invasive in India. They might be invasive elsewhere. A very, very important invasive species in Australia is what's called the cane toad. And that toad, actually very, very recently, they found cane toad. I'm sorry, I couldn't hear that very clearly.
No, Umesh it was unmuted by mistake.
Oh, I've been muted?
No, no, no. That person unmuted by mistake. We are good to go.
Can you type that into the chat box? Oh, the person unmuted by mistake. Okay. Any other examples of invasives in India? But about the cane toad, Nafisa, the cane toad has moved into Australia, and it was taken to Australia to control this particular beetle that was a pest on sugarcane. And then the cane toad has completely taken over large parts of wetter parts of Australia. And they recently found a cane toad that was 2.7 kgs in weight. So they're really adapting very well to this new environment. The red-eared slider, it's huge in the wildlife trade. And often what people do is they buy these red-eared sliders and then they're unable to take care of them. So they release them into the wild. But I don't think it's become invasive. It's an exotic. An exotic is a species that is not found in a particular habitat. It's found in some other location. It's found in some other, for example, a bird that is native to India, like a parakeet, the rose-ringed parakeet, would be an exotic in Europe. It would be an exotic in America. But if it really spreads and it either in the case of plants, it overtakes habitats, it completely dominates habitats. Or in the case of animals like birds, they outcompete native species and reduce the populations of native species. Then they start becoming invasive. Plants, any other examples of plants in India that are invasive? I'll type in a couple of examples in the chat. But Eupatorium, absolutely. Eupatorium odoratum or Crobolida odorata is another very invasive species in this country. Often what happens is whenever land is cleared or land is abandoned, these invasive weeds come in and take over, and they prevent the establishment or the re-establishment of native vegetation. There is another one that I've typed in there, Ageratum conizoides. Again, brought in as an ornamental plant because people thought the flowers are very pretty, and they've taken over a lot of habitat, especially disturbed habitat. You'll often find these invasive species on the sides of roads, for example, or in a field that has been harvested and then left all these invasive species then start taking over those. What's common to all of these invasives here in India? You look at these examples, right? Ageratum, Eupatorium, Lantana, Parthenium, Prosopis, water hyacinth. What's common to all of these? Can anybody guess? There's another.
Beautiful flowers.
Yes, they're all right. Do you know where they all come from? I've just added another invasive plant there called Mycenia micrantha. Do you know where the origin of all these plants is, invasive plants? Where are they native to? Were these planted during British times? Yes, some of them were definitely planted during British time. Saravanan, yes, they're from the neotropics. So they are from Central and South America. And they've either been accidentally introduced into this into India, or they have actually, like Nafisa is pointing out, brought by maybe the British had planted as ornamentals, and now they've taken. Why do you think that these invasives do so well in a new location, whereas in the natural habitat, if you go to the natural habitat in the neotropics, they're not taking over large areas, right? They are not completely proliferating to the extent that they suppress all the other native vegetation. But when they come here, they do that. Why do you think that is? Why do you think that when some exotics move to new locations to which they are not native, they're able to proliferate in such a way? Because native species have not been adapted to them. Yes, they have not co-evolved together. So in evolutionary terms, they have not had the chance to co-evolve, to, well, get used to the presence of each other. So that's definitely one reason. Yes, the environment is suitable. The environmental characteristics are probably the same as the environmental characteristics, or very, very similar to the environmental characteristics from where they came in the first place. And there is little or no competition because there's been no co-evolution with the species in this location. And so there are no competitors to be able to. And absolutely absence of predators as well. There might be certain predatory species like beetles or butterfly larvae where they are found that eat them and keep their populations low. But once they come here, there are no predators that can keep their populations in check. So all of these are factors in the establishment and spread of invasive species. Interestingly, in general, of course, there are exceptions to this. Interestingly, from the New World, or the neotropics, called the Americas, the New World, North, Central, and South America, the New World. The rest of the world is the Old World. It's a old colonial construct. But most of the invasives that we see are plants coming from the New World to the Old World and then proliferating. But it's the other way around for mammals and birds. So it's actually Old World mammals and birds that have been taken to the New World that then become invasive there. Can you think of an invasive bird, bird that is native to India but has been introduced elsewhere and become invasive? Or a mammal, red-belted bulbul? Yes, in certain parts of the US it is invasive. Well, you don't have to be sure. This is you can just take guesses. That's perfectly fine. The red-whiskered bulbul, in fact, is a larger invasive than the red-belted bulbul. Mammals, can you think of any mammals that have become invasive? A mammal that has been introduced somewhere and then completely destroyed native bird nests. Mammal native to India. No, actually, the mongoose is invasive in the Caribbean islands, Jamaica, for example. And a lot of these invasives are because we have moved them around. Humanity has moved them from place to place. So the mongoose, for example, was moved to Jamaica to keep rat populations under control. But then the mongoose is also a very effective predator of bird nests that are either built on the ground or close to the ground. So they've caused declines in bird populations. Another bird, well, a bird that has become invasive is the common myna in many parts of the New World. The Hawaiian Islands, for example, the common myna is an invasive. Just as an interesting sort of aside, everybody's heard of Shakespeare, right? Shakespeare, the British playwright, the English playwright who wrote plays long time back. And in his plays, he mentions a number of birds that are found in England. And when the British went to the Americas and they colonized North America, somebody had this idea that just to feel more at home, these birds over here that we see now in America are all new. They're not like the birds that we find in England. Let's bring all the birds that Shakespeare mentions in his plays to America so that we feel more at home. We feel, oh, this is a bird that's familiar to me. And it's in the, it feels more like England now. And so they brought a lot of species. They brought, for example, starlings and robins and so on. And the common starling is today one of the most abundant birds in North America. It's not a native, but you see it all over Canada and the United States. So, there have been reasons for the introduction of invasive species that are as trivial as saying, let's bring species so that we are familiar with to this new location so that we feel more at home over here. All right, let's move on from invasives. Rock dove. So the blue rock dove or the blue rock pigeon is a bird that is native to the country. It is before all of this building happened, before all of this boom in urbanization happened, the rock dove used to nest on cliffs. And once we started building these high rises and apartment complexes, they became they're very similar to the suitable habitat for these rock doves to nest on. And so they become what's called feral. And we really today cannot distinguish between feral rock doves and actually wild rock doves. So I don't know how many of you use something called eBird. eBird is this online platform where you can upload lists of the birds that you have found when you go bird watching. You go bird watching for an hour, and you record all the species that you see, and you upload your lists onto eBird. Even in eBird, we can't, because we cannot distinguish between what are feral rock doves, which have basically occupied human habitats and become very abundant, versus what are wild rock doves. So the rock dove has taken advantage of habitats created by human beings that are very, very similar to their natural habitats and exploded in their populations. The OO went extinct because of a number of factors. Invasive species, the spread of malaria, avian malaria, because mosquitoes were brought to the Hawaiian Islands with malaria. Hunting as well because of the feathers that were used in ceremonial dresses and so on. So a variety of factors has led to the extinction of Hawaiian birds. Not just, also habitat loss, clearance of their habitats for pasture land, especially to farm cattle, has also been an important reason. So actually, Hawaiian birds it's been this mix of multiple factors: disease, invasive species, habitat loss, and so on, that has led to their declines. All right, let's move on to what we will cover today. We'll look at how we study climate change, because the mitigation of climate change, how we deal with climate change is an entirely different matter. But what we're going to talk about today is how do we figure out what are the studies that have been done to try and understand the impacts that climate change is having on biodiversity. We'll look at habitat loss and degradation of the two very important forms of tropical forest habitat loss and degradation. But any habitat, any natural habitat can be lost, whether it's mangrove or grassland or coral reef or whatever. But we look at forest habitat loss and degradation. The two most important causes for that are fragmentation and selective logging. We'll look at fragmentation. We'll look at overexploitation or the unsustainable use of natural resources through fisheries and hunting. What impacts could that have on natural system? We won't talk about invasive species in much detail because we might not have the time. And then we look at some joint impacts. Species are not just facing climate change. Species are not just facing habitat degradation in separately, right? So any species is facing both climate change and habitat and loss and degradation at the same time. So does habitat loss complicate the impacts of climate change? What are the joint effects of climate change and habitat loss on species? What are the joint effects of overexploitation and habitat loss on species? We'll look at some examples of that as well. So we're going to look at climate change, we're going to look at habitat fragmentation, we're going to look at overexploitation, and then some joint or interactive effects of these species, of these global change drivers. These are called global change drivers. I'm going to look at some of these impacts of these global change drivers on biodiversity. And again, this is all open for discussion. Please do type into the chat box, and we can have back and forth on all of these issues. What you see on the right in those photographs on top is a habitat fragment. So that's a patch of forest that's left over in an agricultural matrix. So you have around this little habitat fragment, little forest fragment, you've got agricultural land, which is unsuitable for biodiversity, for forest diversity. So it's what's called a hostile matrix. And within this hostile matrix are embedded patches of forest or fragments of forest. What you see at in the middle here is this huge overharvesting of marine fisheries. And you can see just one trawl boat, how many fish it can extract, how many and harvest from the sea. So that's a really huge problem with overexploitation with fisheries. Can anybody identify what that snake is at the bottom of the screen, bottom right in the screen? No? Not a snail-eating snake, although it does look very much like a snail eater. Any other guesses? Guess as much as you like. The reason it's there is because it's a huge invasive. It is a type of cat snake, yes. It is a type of cat snake, and it belongs to the genus of cat snakes called Boiga. But it's not called a cat snake. The English name is not cat snake. Absolutely, Nafisa, you're spot on. It's the brown tree snake. Brown tree snake is native to Northern Australia and other parts of that region. During World War II, the United States established a military base on an island in the Pacific called Guam. And there were a lot of bird species that were endemic to Guam. They were only found in Guam and nowhere else. These brown tree snakes were inadvertently transported by ship to the island of Guam. They have become invasive on Guam, and they have led to the local extinction of a number of bird species in Guam, number of endemic bird species in Guam that have been lost forever because these brown tree snakes have just exploded in numbers and predated on their nests and young ones. So this is a classical example of an invasive species. So if you're really interested, do look at the example of Guam and the brown tree snake and the introduction of the brown tree snake on Guam. All right, let's get to climate change. This is a graph showing surface temperature change over time. So the x-axis is time, the y-axis is temperature change in degrees Celsius And you can see that from 1850 to about 2000, there hasn't been much change in global surface temperatures. Although at the end, after the 1950s, you're seeing this rapid increase in surface temperatures, and we're seeing these rapid increases in surface temperatures even today. And climate change is becoming more and more rapid, more accelerating faster and faster. And the Intergovernmental Panel on Climate Change has projected what might happen in the future under certain emission scenarios or certain energy scenarios. And those are called representative concentration pathways, or RCPs. Yeah. So you have RCP 2.6, RCP 4.5, 6.0, 8.5, and the IPCC's models of climate change, these are all based on models that assume certain things. How much fossil fuel will we continue to burn? Will we move to renewable sources of energy? How much forest is going to be left? How much forest is going to be cut down? And so on and so forth. So there are multiple things that go into these models. And if we continue to burn fossil fuels at the rate at which we're burning, climate is going to change in a certain way. If we're able to move to renewable sources of energy and completely eliminate our dependence on fossil fuels, then climate is going to be look in a certain way in the future. And so, for example, with RCP 2.6, we see very, very minimal increases in surface temperatures by the year 2100, maybe, about 1 degree Celsius. Can anyone tell us what is the target that has been set by the Paris Agreement for climate change? By how many degrees do we need to limit climate change? What is the target? Target set by the Paris Agreement that we should not exceed warming by a certain amount. Any idea what that number is? How many degrees Celsius? Absolutely, 1.5 degrees Celsius, which is looking more and more unlikely now, because we have not really reduced our reliance on fossil fuels to be able to generate electricity. 1.5 degrees is or was the target, continues to be the target, but does not look likely that we are going to be able to remain within 1.5 degrees Celsius. And depending on how much we continue to burn, for example, RCP 4.5, 6.5, 6.0, 8.5, with 8.5, we might even have increase in surface temperatures by 8 degrees Celsius, which is a huge amount. That's by 2300. And all of these things are going to have any kind of climate change. RCP signifies representative concentration pathway. Stands for representative concentration pathway. It's the amount of energy that the Earth is receiving per unit area. So the greater the value on the RCP scale, the more the energy that is restricted to the Earth's atmosphere. So that's what RCP stands for. And so under different scenarios of the amount of energy that's going to be on the Earth's surface, we have different projections for what future climate is going to look like. Okay. By 2100, RCP 8.5 predicts that Earth's surface temperatures will be 4 degrees Celsius warmer than it is today. 4 degrees Celsius doesn't sound like too much, right? But it's a huge increase in surface temperatures. And the amount of energy that is added to oceans, for example, because of this heat, really increases the chances of extreme events. Extreme events being extreme rainfall, hurricanes, and things like that. How do you think species might respond to climate change? What might species do to be able to deal with climate change? Imagine you're in a particular habitat, you're a forest bird somewhere, and it's getting warmer and warmer. What could you do to deal with that? Migration, you could shift, you could move to where it's cooler, right? Migration. Okay, let's distinguish migration and what's called range shifts. Yeah, migration is an annual phenomenon. You breed at a certain location, and then you winter in some other location. Usually, you're breeding at high elevations, wintering lower down, or you breed at high latitudes, temperate regions, and you winter in the tropics. That's an annual cycle. Yeah, and yes, migration timings are changing because of climate change. That's definitely happening. But what you can also do is, if you live in a certain location and it's getting too hot for you, you can move to another location. You can shift your range itself in response to climate change. What else can a species do to deal with climate change? Let's look. Here's an example of 3 species of fish and shellfish that are commercially important and people have been catching them. Adaptation, right? Adapt is another way in which you can deal with climate change. We'll talk about adaptation in a bit, but the point about adaptation is, if you have a population of organisms, let's say a population of some bird, right? If the rate of climate change is slow, then potentially they could adapt, because over time there will be selection in that population for certain traits that allow these species to adapt to that changing climate, and therefore they don't need to move. Yeah. But if the rate of climate change is very, very fast, there might not be enough time for that population to for selection to operate on the variation in the population, and then if the rate of climate change is very, very fast, you might have species either going extinct because they can't adapt or being forced to move. But we'll talk about that. So this is the east coast of North America, and you have 3 species here: the American lobster, the red hake, and the black sea bass, all being important for commercial fisheries. And what you're seeing in the dots are colored based on the species, right? So you have American lobster, red hake, and black sea bass. And the dots represent the center of the range of the species, right? And as you can see here, these dots are moving northwards over time. So you got at the bottom over here, you've got 3 graphs, right? You've got from 1970 to 2015, how many miles has the range of this species moved northwards? So it's getting very warm where they are. As it gets warmer and warmer, if you need to seek cooler waters, you have to move north, right? The further north you go from the equator, the cooler it gets. The further south you go from the equator, also the cooler it gets. But in this case, you have waters warming, and if I am adapted, let's say, to 11 degrees Celsius, yeah, and now it's become 13 degrees Celsius. To find 11 degrees Celsius, now I need to move north. So I need to shift my range to a higher latitude. So you have range shifts towards the poles, and you can see over here that over time, those circles are getting darker and darker, right? So the darker the circle, the more northern the center of the range of this species is. So all these 3 species that are commercially important, and we have the data because they're commercially important, because they're caught, right, are moving northwards. They're moving towards the poles. So you see this poleward range shift where species are moving away from the equator. They're moving towards either the North Pole or towards the South Pole, depending on where they're found. But they're moving away from the tropics and closer to the poles, and these are called poleward range shifts. Yeah. You can also move to deeper waters, and deeper waters are cooler, right? The surface is warm. As you go deeper into the ocean, it gets cooler and cooler. And this is an example with the cod in the North Sea. The North Sea is between Scandinavia and the British Isles. And cod is a very, very important source of food. It's a very important food fish for people there. And what we're seeing, if you look at these graphs, there's not been much change in. There's also change in latitude, as in the cod is moving northwards over time. Time is on the x-axis. The cod is moving north over time. It's moving away from moving towards the poles, but it's also moving to deeper waters. So if you were fishing at about 90 meters below sea level for cod all these years, since 1980, 1990 onwards, cod also seem to have moved to deeper waters. So that's another way in which animals are adapting to climate change, especially marine animals, that if they're able to move to deeper waters and survive in deeper waters, then they're able to move there. So that's what's happening in the sea. What do you think is going to happen on land with land animals? We've seen poleward range shift. We've seen species moving towards the poles, and we've seen species moving to deeper waters in the sea. What do you think is going to happen to land animals or land plants? No, nobody. Will they move? Can they move? All right. Here's an example. If you look at terrestrial biodiversity, yes, absolutely. They will move higher or lower in elevation gradient, and this is what we've come to over here. And that's exactly what we're going to talk about. If you don't look at this right now, but if you look at a map of the world's terrestrial biodiversity, most of the world's terrestrial biodiversity is concentrated in mountains. So mountains are only 25% of the world's land area, but they have about 85% of the world's vertebrate species. So mountains are disproportionately biodiverse, especially tropical mountains are disproportionately biodiverse. But this is an example from the Andes with birds from the Andes. You can see on the left is the Andes mountain range. It's found along the west coast of South America. And here we're looking at this particular location here in Peru, which is this range, which is part of the Andes. And so what these scientists did, Benjamin Freeman and his colleagues, went and surveyed birds from low elevations to high elevations. Yeah. This same transect, this same location had been surveyed in the past, for 40 or 50 years in the past. And then it was repeated by Ben Freeman and his colleagues recently. And they asked, have the elevational ranges of these species actually shifted upwards or downwards because of, potentially because of climate change? Yeah. And what you're seeing in the graph below is species. Each bar represents a species. Yeah. Now, let's look at this species here. Yeah. The gray shows what was the elevational range of this species 40 or 50 years ago. So the elevational range of the species, the base of the mountain starts from 470 meters, and the elevational range of the species was 470 to about 800 meters. Right? So it is found from 470 to 800 meters on that mountain. Right? So 40 or 50 years back, if you moved up the mountain to 1,000 meters, that species would not be present because its elevation range was 470 to 800 meters. Today, what's happened to this species is that the upper limit of its elevational range has moved up. So it's gone up to 1,400 meters, all the way up to the top of this mountain. So the upper limit of the mountain is this mountain range is 1,400 meters, 1,400 meters above sea level. So the upper limit of its elevational range has moved from 800 meters all the way up to 1,400 meters. Yeah. Let's look at this species here. The lower limit of its range has moved from 800 meters to over 1,000 meters. The upper limit has also moved up to 1,400 meters. So this species, what it's doing, what's happened over time is that not only has its lower limit gone up, its upper limit has also gone up. So the entire elevational range of the species has moved upwards. Yeah. So species are moving up in elevation in response to climate change. So if I'm adapted to 23 degrees Celsius, 50 years back, 23 degrees Celsius was found at 500 meters. So I used to occupy 500 meters in elevation. Now with climate change happening, 23 degrees Celsius is no longer at 500 meters. Today, 500 meters has a temperature of 25 degrees Celsius. If I need to find 23 degrees Celsius, then I need to move upwards. So if now 23 degrees Celsius is at 1,000 meters, I move up to 1,000 meters to find my preferred temperature. And now, I just remember this could be either direct or indirect, right? As a bird, I could be very a thermal specialist. I could be like, I physically cannot tolerate these warmer temperatures, and therefore I need to move higher up. Or it could be indirect, in that I eat something, that something likes 23 degrees Celsius. So even though if it warms, I'm not really affected directly. I need to move to track my resources. I need to move to where what I eat is found. So this is upslope movement in mountains, and there's evidence for this upslope movement from all across tropical mountains. You know, Papua New Guinea, Himalayas, Andes, for example. So there's very good evidence. African mountains, that species are moving up. But species are moving up at different rate. The way in which species move up differs for species. If most of the species try to move towards an upward elevation gradient, wouldn't the niche trout how they tackle competition with other species? That's a great question. The answer is we don't know. We are just beginning to study these things. And if you're really interested in climate change, and you're really interested in conservation biology, and you're really interested in doing a study on species interactions and how those change because of climate change, then this is really at the cutting edge of the science. The answer is we're still finding out, and we'll get to that. We'll talk about that a little bit here, in the next slide. But what I want to emphasize here, again, this is the same study from the Andes. You can have species that are at the bases of the mountains, right? Low elevation species. You can have mid elevation species that are occupying the middle of the mountains. You can have high elevation species that are near the mountain tops, mountain summits. What's happening with low elevation species is that they're expanding their ranges upwards, but the upper limit of their range is moving up. So their range extent is actually increasing. So if you look over here on this graph over here, if you see the change in elevational extent, is the elevational range becoming smaller or negative, less than 0, or is the elevational range becoming larger or positive, greater than 0? On average, the low elevation species are increasing moving the upper limits of their ranges upwards. Yeah, and so their range sizes are actually increasing. For mid-elevation species, both the lower limit of the range and the upper limit of the range are both moving up. And so on average, the range size is not increasing, but the range is moving to higher elevations. For the mountaintop species, there's a problem because there's nowhere left to go, right? You can't, above this, it's just sky. So when this lower limit of the range moves up, the elevational extent is becoming smaller and smaller. Like you're seeing here, it's becoming negative, right? Becoming smaller and smaller. And the species basically gets squeezed at the top. Once you get squeezed at the top, there's nowhere left to go. What happens? Extinction, local extinctions. So actually in the Andes, we've seen that seven of these mountaintop species have gone locally extinct because as they move up, there's nowhere left to go. There's no higher elevation areas to occupy. And so they've gone locally extinct. Saravanan, this is coming to the issue that you raised, right? Now you've got this mountain, yeah? And you've got low elevation species, you've got mid elevation species, and you've got high elevation species, right? And species are going to move up at different rates. Some species are going to move up very fast. For example, this species is going to move up very, very fast from low elevations to high elevations. Every species is not going to move up at the same rate. Yeah? Some species that are very, very thermally constrained, very, very sensitive to temperature, will move fast. Will move fast up here. Some species are not very sensitive to temperature, but they are intermediate sensitive to temperature. They'll move slowly. So this species will move from low elevation all the way directly to the highest elevation. This species might move from low elevation to mid elevations. Other species might not be thermally sensitive at all. So they might be, it's okay. It's increased in temperature by 2 degrees Celsius at this low elevation, but I can deal with that. So this species might not shift its range at all. So what's happening at high elevations, we know, is extinction, right? Species are moving up to the mountaintops and going extinct. And then with this movement at different rates, you've got this happening now. You have at these mid elevations and at these high elevations, new interactions between species, right? Two species that would have never met each other. I'm saying met each other in a very loose way, but two species that would have never been at the same elevation in the past are now at the same elevation because of climate change. Yeah. And because now they're at the same elevation, there's a new interaction going to happen between those two species, right? Is that going to be competition? Is that going to be facilitation? One species might even help another species to forage, for example, in mixed species bird flock. What is going to happen with these new interactions between species that are encountering each other perhaps for the first time in their evolutionary histories? We don't know. That is something that we're studying now. At low elevations, what's going to happen to species? Low elevation species are going to move up. A very big concern is that there's going to be nothing from that is going to be able to replace species at low elevation. From where are other species going to come into these low elevations? And therefore, it's likely that you see a loss of species at low elevations. There are a loss of species interactions. And what does that mean for species? Does the loss of interactions mean that the impacts on this species is going to be negative or positive? We don't know. We're just beginning to find out. Let's just take a 5-minute break here. And what is the time now? It's 11:25. Let's meet at 11:30. I'll come back at 11:30. And Lachotan, we'll pick up from your question here about the different rates of movements for plants and for frugivores, for example. Sorry, just a minute. I'm having a little trouble with my video. You can see me right now? You see me?
Yes.
Okay,
Yes.
thank you. Let me just share that screen again. Oh. Can you see my screen
Yes.
and the video?
Yes, both are visible.
Oh, okay, because I can't see my own video. Fine, it doesn't matter. Let me find that chat box. Right. So, yes, it is fascinating how these species also adapt to their food resource. You know, plants can't and will not probably move as fast as birds can move, for example, or insects can move, right? And then you have these interesting situations that can potentially arise where a bird that eats fruit and relies on a certain species of plant or a certain set of plants is temperature stressed at a certain elevation. And it can move up to escape that temperature stress. But if it moves up, the plant resources, the food resources that it depends on, it doesn't find any at the higher elevation because the plants cannot move up along with it, right? So what's happening to interactions between species in terms of predator prey, food consumer, competitor facilitator, symbiosis? We're just starting to now begin to understand what is going to potentially, we have expectations of what might happen, but empirical data, as in actual studies, there are some that have looked at poleward range shifts with plants and pollinators, butterflies and their host species that move up. And if you're interested in one or two of those examples that have come out recently, please email me and I will send you those examples of how we have for two species interactions, plant and butterfly, what's happening with poleward range shifts. We still don't have much evidence when it comes to upward range shifts in the mountains, which we really need to understand because mountains have most of our world's terrestrial biodiversity. And we need to understand how this terrestrial biodiversity is going to be able to deal with climate change. And if you're interested in climate change, this is a very, very, you know, very, very, cutting edge area of research for climate impacts on biodiversity. All right, now I'm going to go through this a little bit. One of the problems with climate change is, and just follow my pointer, please. This graph is a little bit complicated, but we'll walk through this, right? Now, if I say habitat has changed, and I want to understand with habitat loss or habitat degradation or habitat disturbance, what happens to biodiversity? Now, in most places, I don't have, uh, let's say I go into a forest and it's disturbed. And I want to understand now, if this forest is disturbed, how many species are lost, for example, or have invasive species coming? Now, I don't know what this habitat was like 50 years ago, right? Before disturbance. If I knew that, I could make the comparison and say, before this forest was disturbed, this was the diversity in it. When the forest is now disturbed, here's the diversity in it. But because I don't know what this particular forest was like 50 years ago, what I do is I go to another forest adjacent to it, and I assume that this primary forest or undisturbed forest gives me an adequate comparison between the disturbed and the primary forest. This is called a space for time substitution. Okay? So the ideal comparison would have been, what was this forest like before it got disturbed? What is the forest like now that it is disturbed? But because I don't know what it was like before, I find another patch of forest that has not been disturbed, and I compare that undisturbed with the disturbed forest. So instead of comparing in time, I'm comparing in space. Now, there is a certain problem here, because with climate change especially, the biodiversity that is found today in undisturbed forest, right, is not actually what it was 50 years ago, even in undisturbed forest. So from the outside, it doesn't look like the forest has been disturbed. None of the trees have been cut down, nothing has been burnt, for example. The forest does not look like it has been disturbed for the last 50 years. But there are unseen impacts of for example, climate change. And we know this from places that have been monitored for a long, long time in terms of their biodiversity, places like the Amazon basin, where historical primary forests, for example, 50 years back, had more bird species than the modern primary forest. But in most parts of the world, we don't have this comparison. And so when we compare modern primary forests with modern disturbed forests, the baseline for comparison has already shifted. So historical primary forest was different from what modern primary forest is because of unseen impacts of climate change. And this is called a baseline shift, right? So climate change is causing baseline shifts in primary forest throughout the world. And those baseline shifts are, in most parts of the world, undetectable. We don't know what those baseline shifts are because we don't have historical data. We don't have data on what these primary forests looked like 50 years ago. So when we're comparing modern disturbed forests and modern primary forests using a space for time substitution, it's important to keep in mind that climate change might have caused pretty large baseline shifts. And so I could say, if in historical primary forest, there were a large number of insect-eating birds, and because of climate change, for some reason, insect-eating birds have declined a lot in abundance and in the number of species of insect-eating birds that are there in modern primary forests. And then I go to modern disturbed forest, and the number of insect-eating birds is low. Then I might conclude, no, the number of insect-eating birds in modern primary is low. The number of insect-eating birds in modern disturbed is also low. Maybe insect-eating birds are just generally rare in this habitat, right? But the comparison I'm making is with a shifted baseline, because in the historical primary forest, actually the number of insect-eating birds in terms of species and population was actually very high. And so we need to keep in mind potential baseline shifts when we're making these space for time substitutions. This is just to say that climate change has already caused hidden impacts in modern primary forests that we are not likely to know about in most parts of the world. Now let's get to habitat fragmentation. Here's a habitat fragment in the foreground. You can see this patch of forest with tall trees. And in the background, right in the back, you can see intact forest, right? It's forest that has not been fragmented. It's forest that is still there, and large tracts of forest. So let's look at the impact of habitat fragmentation. What do you think will happen with habitat fragmentation? What do you think is, if you were to compare that large forest patch at the back and this forest patch in the front, what differences might you see between these two? Lakshmi, could you elaborate on that? What do you mean by canopy stratification? Do you see more stratification in the primary forest versus the fragment, or the other way around? Okay, let me ask another question. Let's say you're looking at birds. Would you find more bird species in the intact forest or in a forest fragment? And why? Why would you find more bird species either in the fragment or in the intact forest? Right. For this image, the primary seems to have more stratification. Yeah, perhaps it does.
So I'm just
Perhaps
gonna
it does.
because it's an explanation I want to give. Am I audible?
Sorry, say again?
Yeah, I'm just unmuting because it's an explanation I want to do.
Right.
Yeah,
Right.
but I think I would see more birds, not in a primary forest, because ideally in a regenerating forest, we should potentially see more stratification.
Sure.
Yeah.
That's a possibility. What do you think about the number of bird species, for example, between the primary forest and the fragment? Which will have more?
I think the fragment would have
Why do you
more
think that? Why do you think that is?
because it's also closer to, I mean, it has more forest types, I guess, and it's closer to the other forest types. And the edge effect might come into play, where more species are, using the habitat to move around and stuff.
Right. Okay. Interesting. Yes, let's look at those. First of all, habitat fragmentation, especially in the tropics, is a huge problem. What we're seeing here is in tropical forest, the distribution of fragments of different sizes. Right? So whether you're in Central and South America or in tropical Africa or tropical Asia, what you have is fragment size on the x-axis, and that's on a fragment size on the x-axis, and you have the frequency of fragment sizes on the y-axis, so number of fragments of a certain size on the y-axis. And what you can see is that there are a large number of small fragments, yeah, and a very small number of large fragments. So what's happening is that vast areas of forests are becoming more and more fragmented. And because they're becoming more and more fragmented across the tropics, you have a large number of tiny forest fragments and a very small number of large forest fragments. Yeah. What does fragmentation then do? Once this fragmentation happens, you have 3 or 4 important impacts on species. One is simply the reduction of area, right? Like you were pointing out, it's just you had 100 square kilometers of forest. Now you have, 20 square kilometer of forest in 4 or 5 square kilometer fragments, right? So one is simply the reduction of area. So you have large, vast tracts of forest that become smaller and smaller. Not only are these fragments smaller, they're also isolated. Yeah. So there's something called the theory of island biogeography. Let me just type that. Theory of island biogeography. Oh, oops. My cursor wasn't there. Which has informed a lot of habitat fragmentation literature and habitat fragmentation studies. And basically, area and isolation are the 2 important components of island biogeography that determine how many species are found on islands And in effect, in most cases, habitat fragments are also islands, right? This habitat fragment here is sort of a forest island in agriculture. Just like an island is a chunk of land surrounded by the sea. So it's isolated. It's isolated from larger patches of forest. And it could be isolated to different extents. You could have fragments that are very close to large patches of forest, or you could have fragments that are very, very far away from. So less isolated versus more isolated. And then you also have very sharp edges between fragments and the surrounding matrix. So where in natural habitats, you generally find that the edge is soft. You have a natural forest, the tree density might come down slowly until it gives way to a grassland. In habitat fragments, typically the edge is hard. It's like here is the forest, and suddenly it stops, the forest stops. And that is what's called a hard edge. And there are effects of the edge being that hard. And then there are other effects as well. But let's look at things like area reduction. This is the island of Borneo, of which the northern part is Malaysia and Brunei, the southern part is Indonesia. And in 1950, almost the entire island was forested. And over the years, what we're seeing is in 2020, a huge reduction in area from 1950. So, more than half that forest has disappeared from 1950 to 2020 in a 70-year period. Borneo has faced a huge amount of deforestation, and just the area of forest that was available has reduced. What does area reduction do? You basically, the number of species that a forest fragment can support reduces with area. This is an example from Tanzania, where you have forest fragments of different sizes. On the map on the right, you can see in black, marked in black, Mololo, Gangao, Buria, Yale, Fururu, Chawuya, which are forest fragments of different sizes. And the matrix that these forest fragments are in is coffee. So there's coffee plantations, and within these coffee plantations, what you have is these tiny little patches of forest, which vary in their sizes. And if you look at the graph on the left, you have area on the x-axis, which is on the log scale. Yeah. And you have species richness, number of species on the y-axis. And as area increases, generally the number of species also increases with habitat fragmentation. So area effects are very important. Sorry. Why do you think that large fragments will support more species than small fragments? If you could type in the chat box, please, why you think large fragments support more species than small fragments. You're seeing this here, right? For all species, as fragment area increases, the number of species also increases. And for forest specialists, the number of species also increases. More resources, yes. More space, more food availability, yes. A forest fragment that is large will have the absolute amount of resources will definitely be larger, greater than in a smaller fragment. And species that will be more niches than they can occupy. That is also a possibility, that as you fragment a forest, the number of niches comes down. But if you think about area or space, and you think about minimum viable populations, right? So let's say for a jaguar, right, or a tiger, the minimum viable population for the tiger to persist is, let's say, I'm just an example, just a hypothetical example, is 10 individuals. You have to have 5 males and 5 females. If the tiger population has to persist for a long time. Now, let's say the requirement for each individual tiger in terms of space is 10 square kilometers. Then you need a 100 square kilometer fragment, or at least 100 square kilometers of forest to support 5 males and 5 females. Yeah. So if your fragment becomes smaller than 100 square kilometers, it is not going to be able to support tigers, right? And so as fragments become smaller and smaller, species that require large areas to maintain minimum viable populations are the ones that will disappear from smaller and smaller fragments. So very often it's the largest species that disappear from forest fragments because those large species require large areas to be able to maintain their population sizes. So that's one important reason why space and the availability of resources determines this pattern where small fragments have fewer species, larger fragments have a larger number of species. So that's area effects, right? So I wondered whether there might be a critical fragment size beyond which we see sharp decline in species diversity. Generally, what you see is this gradual decline in species diversity. It might depend from species to species. For example, the pattern with birds might be different from the pattern with plants, which might be different for the pattern with amphibians. I have not come across a critical threshold, where you're saying that if the habitat fragment becomes smaller than 10 hectares, then we should see, a drastic decrease in species diversity. Coral, you do have coral island, coral fragments. Can you elaborate on that? So what's happening with coral, of course, across the world, especially because of climate change, is coral bleaching. Coral is a symbiosis between an algae and another organism. And what happens with bleaching is that the zooxanthellae, which actually produce the color in coral, leave the coral. They're expelled from the coral body. And because those were the organisms that produce those beautiful colors in coral, when they leave, the coral becomes bleached or becomes white. It looks white. And then you have certain patches of coral that are not bleached. So it could be, because if you could just elaborate on that while we continue with habitat fragmentation, we'll discuss coral as an example potentially. The second thing that fragmentation does is cause isolation. So this fragment is isolated, right? It's isolated from another larger patch of forest. And what does isolation do is that it causes impacts like this. This is from the Amazon basin. What you're seeing on the right is forest through which this mud road has been built. And then you have these territories of birds in the forest. And when fragmentation happens, even with these mud roads and roads that you think, oh, this is not a 6-lane highway, right? Species should be able to cross this road from this part of the forest to this part of the forest. So you've basically got a large fragment here and a large fragment there. This should really make a difference. Species should be able to move across these. But for a lot of tropical species, actually, even that thin road going through the habitat has huge examples. So when you build a road, the territories of these species becomes the road. They're not able to move across those roads, even that small road at all. So even if you have in tropical forest these fragmentation arising from roads, and one of the main reasons for fragmentation is roads. And you have this road coming through, even if the canopy is touching on the top and you think, oh, this road is not really important, it really does stop. It really becomes a hard boundary for species territories, even if the road is not tropical species that are adapted to especially the understory, which is warm, wet, dark, are very, very reluctant to cross even these tiny roads. So movement between patches is a huge problem. Fragmentation also affects species interactions. And this is an example with what is called mixed species bird flocks. Mixed species bird flocks are associations between multiple species. It's not like a flock of sparrows or a flock of pigeons. These are interactions between multiple species. You could have up to 20 or 25 species in a single flock, and this flocking species, they feed together, they move together, they provide either access to food to other species in the flock, or they provide protection from predators to other species in the flock. So what you're seeing here in primary forests on the left is this network between species. Each of these circles is a species, bird species, and it has certain interactions with other bird species. And you can see this very complex web of interactions between the species, different species in this flock. And those complex interactions are very important for the survival of the species that participate in these flocks. Now, from primary forest, you move to a fragment, which is 10 hectares, and you see a large breakdown in these species interactions. So you see that where you have this very complex web of interactions that provides all these benefits, protection from predators, access to resources, that breaks down in a 10-hectare fragment. And the breakdown of these interactions can lead to lower survival, can lead to certain species even going extinct in the forest fragments. Right? So there are many mechanisms through which forest fragmentation acts to reduce species richness, to reduce the number of species. One of them could be the breakdown of interactions between species in forest fragments. So because it's below a certain coral spread, it cannot support other organisms, like we see small solitary organisms around coral reefs. Right. So again, sorry, I'm not very familiar with the coral literature and coral fragmentation, but you're certainly right in that you would expect that the smaller the patch of coral, the lower the number of species they could support, for sure. But I don't know whether there is a threshold where you're going from, 100 square kilometers of coral, lower and lower and lower, and suddenly if you reach, 1 square kilometer, does the species just suddenly drop? That is something I don't know. I can find out and let you know later. All right, there is something very interesting happening with fragmentation, something very important happening with fragmentation called extinction debt. Now, what does that mean? Extinction debt. When a forest is fragmented, when somebody goes out, fragments the forest and creates a habitat patch, a forest patch, you don't immediately see all the species going extinct, right? So like in the tiger example, if you need 100 square kilometers to support a tiger population of 10 tigers, if you suddenly reduce the habitat size to 80 square kilometers and you go in and count the number of species, you might still find tigers immediately after fragmentation, right? The tiger population has not gone extinct in that fragment. So immediately after fragmentation, there will be a certain number of species in that fragment. But over time, the species that cannot persist in the fragment will go extinct in the fragment. So there is an extinction debt to be paid. There is a certain period of time over which species will go extinct in the fragment. And then the fragment will end up being able to support only those species that it can potentially support. This is an example of plant species richness from the Amazon. If you look at species richness in 2003 across a forest area, so you have fragments of different sizes on the x-axis. It's just on the log scale. So it's the log forest area in hectares on the x-axis and plant species richness on the y-axis. 2003, just after fragmentation, you have this certain pattern, right? You expect that the number of species will increase with area, and you do see that the species richness of plants is increasing with the area of the fragment. But you come back in 2013, And you see that the number of species actually gone down consistently in these fragments, right? So it's not as if as soon as you fragment a habitat, the number of species immediately collapses. There is a certain extinction debt to be paid because of fragmentation that takes a certain amount of time, and after a certain amount of time the fragment is left with only those species that can possibly persist in those forest fragments, and this is a phenomenon known as extinction debt. Again, this is extinction debt in Southeast Asia, where the building of a dam created this lake, and in these lakes are and within this lake are actual habitat fragments or actual islands now created because of the creation of this lake. And you go on into these islands and you count the number of small mammals on large and small islands. 5 to 7 years after these islands are isolated versus 25 years after these islands are isolated, and you're seeing that from over a 20-year period, you're actually losing these mammals because immediately after fragmentation, you don't lose everything. It takes some time for the species that are intolerant to fragmentation to actually go locally extinct in these fragments. Let's get edge effects. Edge effects are important because the edges are more exposed to abiotic factors. They tend to be drier, they tend to be warmer, and windier because they're not buffered by any other vegetation, for example, right? So the trees along the edge of a forest fragment, for instance, are more vulnerable to fire. They're more vulnerable to being taken down by the wind. They're more vulnerable to desiccation. And the edges also encourage the spread of invasive species because the edge habitat is now altered and it often becomes more suitable for invasive species. And the problem is that edges are increasing all across the world. So this is a map of forests across the world that is color coded based on the different of the distance of that forest patch from the edge of that forest patch. You can see that basically where do you see forest patches that are more than 1 kilometer from an edge, right? So forest patches that have an interior that is more than 1 kilometer from the edge, basically you're seeing that in the Amazon basin, you're seeing that in the Congo basin, you're seeing that in certain parts of Southeast Asia and northern Myanmar. Whereas you see most of the forest in the world is actually very, very close to an edge. And the closer you are to an edge, the more likely that these detrimental impacts of forest fires, invasive species, and so on and so forth are going to affect species. So edges are increasing worldwide, and that is a cause for concern because edges then, not only are there edges that but those edges also increase the chances that there will be other things happening there that are detrimental to biodiversity, things like fires. And finally, other effects, just briefly touching upon the other effects that fragmentation has. Fragmentation encourages more fragmentation, and this is what's called a fishbone pattern in fragmentation. You will often find in the fragmentation literature a certain phrase saying that the first cut is the deepest. This is an example again from the Amazon, where you have this road being built that fragments then the habitat into two patches, but the very existence of the road encourages people to settle on these in these areas, and then they build secondary roads that then fragment the habitat even further into smaller fragments. So fragmentation, this road created two larger fragments, but the presence of this road encouraged smaller roads to be built that then create these smaller fragments. So fragmentation encourages fragmentation. That was habitat fragmentation. Let's quickly look at overexploitation. And overexploitation is especially a problem with fisheries. What you can see here is a shark fishery. Sharks are an important source of revenue for fisheries, especially illegal shark fin harvesting for shark fin soup, which is popular in China and Southeast Asia. And really, the number of sharks that we're taking out from the ocean appears to be highly unsustainable. We'll start off looking at fisheries when we're talking about unsustainable harvest or over exploitation of natural resources. Since 1970 to almost the present, in 2015, just the amount of fishing has increased in intensity 18 times. The effort that is being going into fishing has increased 18 times over this 45-year period. And you can see that even single trawlers can harvest huge amounts of fish. And we're also harvesting larger fish, like sharks that you can see at the bottom over there. But over time, what's happened with fisheries is that the larger fish have been fished out. And so we're fishing down the web. You deplete the populations of larger species and higher trophic level species. And then the fisheries are then targeting smaller species at lower trophic levels. But fisheries pressure has really increased drastically over the last 45 or 50 years. And if you look at shark and ray populations, this is from the Living Planet Index. From 1970 onwards, whichever ocean you go to, the Atlantic Ocean, the Indian Ocean, or the Pacific Ocean, shark and ray populations have collapsed quite dramatically. It doesn't matter if you're a large shark or a small shark, doesn't matter if you're a tropical shark or a temperate shark, populations of these sharks and rays have declined very, very dramatically. And so overexploitation is a huge problem. And that can cause what are called trophic cascades, especially if you take out the apex predator. Here is an example from the Gulf of Florida, where if you look on the right, you have the blacktip reef shark that feeds on what is called the cow-nose ray. So it's a predator of the cow-nose ray. And the cow-nose ray is the secondary consumer that feeds on mussels, which is the primary consumer here at the bottom right. Now, fishing in the Gulf of Florida has caused, over the years, the population of the apex predator, which is the blacktip reef shark, to come down to almost zero. Yeah. Basically, there's been overharvest, unsustainable overharvest, and the apex predator is almost absent from the Gulf of Florida. Because the apex predator is absent, the control over the population of the cow-nose ray has now been removed, and the population of the cow-nose ray has really shot up over time. So as the apex predator declines in abundance, the abundance of the secondary consumer, the cow-nose ray, increases. And as the cow-nose ray populations increase, the populations of the primary consumer that the cow-nose ray feeds on, which are the mussels, have also gone down. So this is called a trophic cascade, where you remove the apex predator, you remove the top predator from the ecosystem, and the next trophic level increases in abundance, and therefore the next trophic level declines in abundance, which leads to the next trophic level again increasing in abundance. So it's a cascading effect that that overharvesting can have on ecosystems, especially where ecosystems in which predation is very important in keeping community structure. So that was fisheries. Let's look at hunting. In the Amazon basin again, people hunt primates, things like spider monkeys, as well as larger bodied mammals like the tapir. Yeah. And these species are very, very important for the regeneration of tropical forests because they're seed dispersers. So what primates like spider monkeys will do is that they will eat fruit and then they will disperse the seeds in a different location through their droppings. Tapirs as well, which are large terrestrial mammals, sort of like analogous to our, I mean, they're like fruit-eating large mammals that will eat fruit that has fallen on the ground and then disperse the seeds of large-bodied, of large-seeded species further away, aiding in forest regeneration. What Carlos Perez and colleagues did was to ask if spider monkeys were completely eliminated. And because spider monkeys are completely eliminated from hunting, right, from overharvest, from unsustainable extraction of these natural populations, what would be the decline in a percentage loss of forest biomass? Because the services that these animals provide in terms of forest regeneration is lost. And then if you lose both the spider monkeys or the canopy, the primates, as well as these large-bodied terrestrial species like the tapir, what is going to happen to forest biomass? And like you can see in this color code, basically anything that's below here is lost. Biomass loss of the forest, of trees in the forest. And so the loss of these smaller primates leads to relatively smaller losses of forest biomass. But if the hunting and the unsustainable removal of species from the habitat includes the complete loss of primates as well as animals like the tapir, then you can see up to 23 to 25% biomass loss in the forest. So hunting can have huge consequences for downstream consequences for just the existence of forests and the biomass of forests. Another thing that is common of fishing and hunting is that large individuals are targeted, right? What you see on the left is an image from Pakistan, which allows trophy hunting, and on the right you see an image from Africa, which allows trophy hunting of individuals. So hunters come and they pay a certain amount of money to be able to go into the wild and to hunt certain species. And whether it's fishing or this kind of hunting, or even hunting for subsistence, if a hunter is going out to hunt to feed, even to feed his family, he would rather use an arrow or a bullet on a large individual than a small individual, because it makes more sense to get more for a certain amount of effort. So all of this kind of harvesting, trophy hunting, fishing, subsistence hunting, typically targets large animals and large individuals. And what that does is that not only does it reduce population density, right? So hunting directly reduces population density. Harvesting reduces the size of the population. But because there are now no longer those large individuals in the population, and the large size gives you better competitive advantages. If you're competing for mates, for example, then the larger you are, the more likely you are to be able to mate successfully and reproduce successfully. And so the harvesting is reducing population size. It's taking out the large animals, but it's also by removing those large animals and leaving behind only small individuals, it's removing the selection pressure for being large, and therefore individual body sizes also are reduced because of hunting. So it has other population level impacts rather than just reducing population density. It also can cause, for example, declines in average body size in the population. Now, regardless of what it is, climate change, habitat destruction, hunting, habitat fragmentation, you typically lose large, higher trophic level species. So let's look at some of these graphs here. What you've got on the top left is climate change and reef fish. And you've got trophic level on the x-axis. So you've got higher trophic levels as you move towards the right. And you've got the probability of extinction from coral bleaching on the y-axis. And the higher trophic level you are, if you're a predator, you're much more likely to go extinct than if you are eating vegetation. If you're an algivore, for example, you're less likely to go extinct from climate change than if you are a top predator. So same thing with logging. If you are large, that's on the left, or the x-axis here, body length on the x-axis. If you are large, you're more sensitive to logging, right? Logging, which is the form of habitat degradation. Larger species are more vulnerable to logging. With hunting, what you see is that body mass on the x-axis, you have steep declines in the body masses of large species or large individuals because of hunting. And with fragmentation, habitat fragmentation as well, if you have body size on the x-axis and you have the probability of extirpation from a forest fragment on the y-axis, you can see that a large animal, a large bird, has an almost 100% probability of being extirpated from a forest fragment here, whereas smaller species have a much lower probability of extinction. So large trophic level, high trophic level species are vulnerable to extinction because of all of these global change drivers. Yeah? And that leads to a process called biotic homogenization, arising from the non-random loss of species. And why is this non-random? It's non-random because it's large high trophic level species that are going to go extinct because of these obstacles, right? So with fisheries, for example, it's sharks, high trophic level apex predators that are vulnerable. With hunting, for example, it's large birds that are vulnerable. What happens here then is, if you just look at the bottom of this graph over here, then you might have three communities, A, B, and C. And those three communities of species, so A has a certain species composition, B has a certain species composition, C has a certain species composition. But if you hunt out all the large animals from A, or climate change affects all the large animals in C, or habitat fragmentation affects all the large animals in B, then the loss of those large animals leaves the communities A, B, and C left with small, low trophic level species. And so therefore, these communities start converging because of global change drivers in their traits. They become dominated by smaller species. They become dominated by low trophic level species. And that's a process called biotic homogenization, because where you had very heterogeneous ecological communities, where you had communities that had very different species, distributions of species traits like body mass, like trophic levels. Now, because of global change drivers, you now have communities being dominated by small, low trophic level species, and then communities are becoming more and more similar to each other over time because of things like climate change, hunting, and habitat degradation. Let's look at some of these joint impacts that you see. And this is hunting of what are called game birds, large birds in the Amazon basin. And it's the probability of it's the abundance of these species on the y-axis on the log scale. And it's a patch area on the x-axis. Now remember, this is not species richness, right? This is the abundance of each of these species. Metu tuberosum is a certain species, Odontophorus guajanensis is a certain species. And you're asking, as the fragment becomes larger, does the abundance of these species also increase? This is not species richness, unlike what we saw with habitat fragmentation earlier. This is abundance of. And you can see here that for all these species that are hunted, abundance increases with fragment size. And the reason for this is very interesting. It's because the smaller fragments actually can support populations of these species, but smaller fragments are also more accessible to hunters than larger fragments. Smaller fragments have much larger boundaries, larger edge, so hunters are able to access these small fragments Whereas the larger fragments, you really have to go deep within to find, it's not as accessible as smaller fragments. And so smaller fragments get hunted out. So this is a joint impact of fragmentation and hunting, right? So fragmentation encourages hunting because smaller fragments are more accessible. And so even though small fragments can potentially support the populations of these species, the populations of all of these species crashes to zero in small fragments because of hunting. Here's another example of joint impacts, which is what's called climate connectivity and land use. Let's look at this upper panel here. And it's color-coded. This map of tropical forests is color-coded based on what is called climate connectivity. Let's look at South America. If I'm an organism here, if I'm an animal here, in the future, can I remain at the same temperature that I am at now by moving, or reach a cooler area by moving? Is that possible? So if it's possible, then you're going towards blue. So animals here have climate connectivity. So if climate change happens, they can potentially move to another location where they find either the same temperatures that they're at now or temperatures that are cooler than where they are at now. If an organism is here, as it warms, they are not going to be able to move to find other locations where temperatures are either the same as where they are right now or cooler than where they are right now. And the reason for that is fragmentation. If you have a habitat that's highly fragmented, then movement between fragments is problematic, right? So the larger the patches of continuous forest, the easier it will be to move to new locations because of climate change. But if the fragments are, if the forest is highly fragmented, like you see at the bottom over here, then you are not able to move. Climate connectivity is very, very low. So now you can see in the face of high fragmentation of forest, most parts of the Amazon, there is no climate connectivity. These organisms will not be able to move to new locations to remain at the same temperatures or to remain at temperatures that are cooler than what they're occupying right now. Let's take a, sorry, 1 minute. Should we take a 5-minute break? And what is the time right now? It's 12:15. So we'll come back at 12:30, 12:32. Just take a short break. If you have any questions or any comments, please do type them into the chat box in the meanwhile. All right, let's just wrap this up. Please, reaching the end of the session, and of course, at 2 p.m. to 3:30 p.m. is interactions with the faculty that you might have selected to interact with. We'll start that session at 2 o'clock. But let's just wrap this up in thinking about joint impacts. And I think the reason why we need to think about joint impacts is that anywhere in the world, in the Anthropocene, species are not facing one or the other global change drivers in isolation. Species are facing climate change and hunting. They're facing climate change, hunting, and fragmentation. They're facing land use change and climate change and hunting and invasive species, for example. So it's not enough now anymore to just say, here's the impact of habitat fragmentation or here's the impact of climate change. It's important to understand how, depending on which location you are at, depending on which species you are planning to study, it's important to say, you know what, I think these are all the effects that the species is subjected to. And therefore, I need to understand in the future what might happen to the species, what might happen to this habitat, what might happen to this ecosystem. And this is one very nice way of thinking about this is, let's say you've got climate change on the left and land use change on the right, and you think about the impacts of these in three ways. Let's look at the left, which is climate change. You have the exposure that the organism is exposed to, right? In the case of climate change, that would be by how much has temperature increased, right? That's the exposure to the organism. That is, the organism is exposed to 2 degrees Celsius increase in temperature, right? So that is the magnitude of the global change driver that this organism has been exposed to. Then you ask, how sensitive is this organism? Yeah. Is this organism highly sensitive? If it is highly sensitive, then that exposure is going to result in some impact, right? It's going to affect body performance, it's going to affect fitness, it's going to affect survival, etc. If it's not that sensitive to that degree of exposure, then it's going to manage, right? It's not, this sensitivity is low. And then you ask, is it adaptable or non-adaptable? If the organism is not able to adapt, for example, I am an organism that adapts to climate change by shifting my elevational range upwards, right? If I can do that very successfully, then I'm adaptable. But let's say I am some kind of plant that can't move higher up to higher elevations because of climate change. I have very poor dispersal ability, then I am non-adaptable, right? Now, if you take the entire area of this triangle with climate change, then that is my overall risk to climate change. The larger this area of the triangle, the greater my risk to climate change. Yeah. Similarly, with land use change, the exposure could be in the form of how much of the habitat is lost. Sensitivity could be like, if the habitat is lost and my prey declines, what is the impact that it has on my survival and reproduction? Let's say I'm a high trophic level species and my prey declines and disappears. Then I have high sensitivity to habitat loss. If I'm a low trophic level species, I might not be as sensitive. And then again, am I adaptable? Am I non-adaptable? Can I survive on human-dominated landscapes? Can I not survive in human-dominated landscapes? For example, there are species like leopards that survive very well in human-dominated landscapes. But there are other species like, like tigers, for example, that are not as adaptable to human-dominated landscapes. And again, the area of the triangle tells you what is your risk, overall risk to land use change. Larger the triangle, larger the risk. So, if you've got this, for example, as an if the exposure is unchanged, climate change is not happening, sensitivity is not changed, but non-adaptability is high, right? The capacity to shift your distribution in response to climate change decreases as land use change reduces habitat connectivity. So, and when you're talking about land use change, you're sensitive to land use change because pay is declining. And climate change, so your loss of habitat is reducing your ability to shift your distribution because of climate change. And climate change is changing your behavior because if it's hotter, you're less likely to be able to hunt because you're going to overheat. So those joint impacts cause this triangle to become larger. And then the total area of those two triangles is your overall susceptibility to climate change and to land use change. So this is one way of thinking about uh, how species might respond to these joint effects. What is the level of exposure that they are facing? Are they sensitive or not sensitive to that particular exposure, level of exposure? And are they adaptable or non-adaptable? And then based on that, you can ask or predict and say, this is what is likely to happen to the species with joint impacts. Now, I'm just going to end by saying, a lot of people are interested, and please do tell your friends also, a lot of people are interested in the impacts of climate change or land use change on biodiversity, right? They're interested in those applied aspects to ask, how does biodiversity respond to climate change? But there are a lot of people who are not actually interested directly in this. They're not directly interested in, does habitat fragmentation cause something? Does climate change cause something? But let's say you're interested in behavior. Yeah. And you're asking a question on behavior saying, if there are 10 species, how are they going to interact with each other? If there's only one species, how is it going to survive in the absence of interactions? Even if you're not directly interested in the impacts of, let's say, climate change on this mountain, right? The fact that climate change is happening, the fact that climate change is causing species to shift their distributions, actually is creating this experiment, right? We are actually creating an experiment where species are moving in response to our to anthropogenic increases in temperature. And therefore, there will be new behaviors that emerge. And there will be behaviors that might die out because those species or those are not species that engaged in those behaviors with each other before are no longer coexisting because of climate change. So even if you're not directly interested in the impacts of anthropogenic global change drivers, the fact that this is happening provides gradients in, say, species richness or behavior that then can be used to study, other things, behavior, community structuring, so on and so forth. So these anthropogenic gradients, unfortunate though they are in terms of reducing biodiversity and generally causing harm to ecosystems, do provide an opportunity to even study fundamental concepts in ecology. So I'll end here and wait for another 5 or 10 minutes to see if people have questions. Please put them in the chat box if you have questions or comments. And you're free to leave. If you'd like to leave now, please feel free to leave. And those who have signed up to interact with faculty at 2 o'clock, please do join the Google Meet links that have been provided to you by email. But this is the end of the morning session. I'm happy to take any questions or respond to any comments if you have them.
Sir, is migration better than adaptation.
Is migration better than adaptation? Because of climate change, you mean?
Yes, sir. Like for the fishes, we were saying they were moving more towards the
Right,
northern areas.
right, right. Um, Depends on a variety of things. There is a paper by, if you just remind me, because you have my email address, just write to me and I will share that paper with you. It looks at whether staying at the same location and adapting to changes in climate, or dispersing because of climate, or doing a combination of both of these things. Which of those three is best? Now, here's the thing. If you are an organism that is mobile, an organism that can move and disperse, then you are able to at least move to adapt to climate. If you are an organism that cannot move, say you're a tiny frog and you can't move at all, then you have no choice but to adapt or go extinct. Right? And whether you are able to adapt or not is dependent on, one, the pace at which climate change is happening. So climate change is very, very rapid. Let's say as an extreme, tomorrow temperatures increase by 10 degrees Celsius, right? You're not going to be able to adapt to that massive increase, sudden increase in temperature, right? And so you'll go extinct. So if the pace of climate change is slow, adaptation is possible. If the pace of climate change is very fast, then dispersal might be the only way in which you could adapt to climate change. But that paper shows basically that if you can disperse and adapt, that's the best. That's the best chance you have in surviving in a warmer world, in a world affected by climate change. But it's very, very species dependent, right? In the Amazon basin, for example, birds are becoming smaller. I mean, it's not like an individual bird is shrinking, but over time, in the population, the average body size of bird species is reducing, and wing length is increasing. And that we think is because larger wings allow you to lose heat more effectively. And so in the Amazon, a lot of these bird species, it looks like because they are unable to disperse very far, a lot of these species don't fly very far. They're very restricted in their dispersal ability. They seem to be adapting. Other species, especially in mountains, seem to be shifting. But there's no one answer whether dispersal is better or adaptation is better. It will depend on the pace of climate change in different regions. It will depend on whether the region is mountainous or not mountainous. It will depend on what the biology of the species is, whether it's a good disperser or a bad disperser. It will depend on what is the inherent variability in traits in the population that allows an individual to adapt to climate change. So there's a great amount of variability, then potentially the population you can select for traits that are effective in adaptation to climate change. So it's a whole number of factors that determine which is better and which actually happens in nature.
So, sir, this would be happening over a long period of time, right? Because if, for example, acclimatization is also a case, like if we hike a mountain, we can acclimatize in a small time.
Correct. So range shifts can happen over short periods of time, and we're seeing those happening over very short periods of time. But they also come with other problems, right? The higher up you go, the less oxygen there is. So there are all those considerations as well. Adaptation generally, the movement of the shift of traits in a population to another trait space generally takes longer, but it depends on the lifespan of the species, right? If I am a species that is very short-lived and the generation time is low, in a 10-year period, let's say there are 10 generations of the species versus a species like an elephant that is very long-lived, right? And generation is slower. The possibility of adapting is much higher in the shorter-lived species that reproduces very, very fast. Whereas a species that reproduces slowly, the possibility of selection when habitat change is very, very rapid is much lower.
Okay, sir.
Sri Kadapati has a question on saying a view on ex-situ conservation. Okay. Okay, I'll say this. See, conservation biology is based on biology, it's based on science, right? So there are ambiguities in the science, there are uncertainties in the science, but it's essentially a process where you're trying to find the truth, right? You're trying to say, if climate change happens, if habitat fragmentation happens, how is this affecting the species, right? And there is a certain way that it is affecting the species in the wild, right? There is a certain true way in which it's affecting the species, and the science of conservation biology is trying to find that truth, right? Now, conservation, on the other hand, is, I think, more of a moral position than a true position, right? Why are you worried? Why worry about the extinction of a species that might contribute very less to an ecosystem? Some people would say it's okay for that species to go extinct. Others would say no, every species has an inherent right to exist, and therefore we should do all we can to prevent the species from going extinct. So, ex situ conservation has succeeded in many, many cases where you have, for instance, species that are on the brink of extinction, and you bring them in to zoos or breeding centers and successfully breed them and reintroduce them to the wild. A very, very interesting example of this is the Mauritius kestrel. Just typing that into the chat box. Mauritius kestrel, which is a bird, and the leader of this effort was a man called Carl Jones, who actually brought in these kestrels and bred them in captivity, and then reintroduced them into the wild. So ex situ conservation does have value in that you can, with vultures, for example, in India, right? With what we're doing is we're breeding them in the wild and then releasing them into the population. So I think it's useful in those cases where populations have crashed to the extent that if we leave them in the wild and don't do any ex situ, don't make any ex situ efforts, then those populations are going to be lost forever. That species might be lost forever. My position is that even if a species is not, if a species, even if a species is not important for ecosystem services, for example, my position is that every species, and this is just a moral position, it's entirely my opinion is that every species has a right to exist, and we should do all we can to prevent extinction, regardless of the role the species might or might not play in its ecosystem. Coming back to food resources for species shifting elevational range, could there also be instances that the species move their food resources with them to the new location? So maybe wait for their food source to occur in the new space. Food rewards again. So let's deal with the first one first, so second one first. So if a species has to wait, I am a frugivore, I am directly temperature stressed, let's say. And I would like to move to a higher elevation, but my food source is not there. Now, if I wait at lower elevations, I might suffer so much thermal stress that it's detrimental to this population of frugivores. If I move to higher elevations, I might not find food. So that seems to be a lose-lose situation for this species, right? If I stay, I'm thermally stressed. If I move, I'm food stressed. There's no food. For frugivores, so frugivores disperse fruit, as we all know. But let's say I have a frugivore and I feed on figs, and I eat figs, move to higher elevation, and disperse the seeds of those figs. But for that plant resource to actually reach, for that fig tree to reach maturity at the higher elevation will take a lot of time, right? So I don't know whether it's possible for a frugivore, for example, to disperse its food source or take its food source to a higher elevation or move its food source to a higher elevation and have it ready in time for it to be able to occupy the higher elevation and still feed.
Sir, what are the orders of shifting ranges? Like, in how much distance do we consider to be at a shifted range?
There's no threshold value for considering the range to be shifted. It's just that we should see consistent patterns in, the rate at which you shift your range is also dependent on a number of things. So as long as you're seeing consistent movement, either away from the tropics towards the poles, or you're seeing consistent movement from low elevations to high elevations, or you're seeing consistent movement from low depth to greater depth, that would be counted as a shift in the range of a species. But it's not like, if it's 10 meters, then that's a range shift. It should be consistent over time, that movement. All right, everyone. There's another one. Would that depend on the temperature or other factors that are important to the species? It would depend on increases in the absolute magnitude of the increase in temperature, definitely. Other factors that are important to the species. So you have species that can be temperature specialists or species that can be temperature generalists. Right? Temperature generalists that occupy large thermal niches can, tolerate increases, some increase in temperature, and therefore don't need to shift as much. But thermal specialists, and most species in tropical mountains are thermal specialists, that can occupy a very narrow range of temperatures. Those will then have to move faster in response to climate change. So it could either be how sensitive the species is to temperature and what range of temperatures the species can actually inhabit, or it could be what is the species eating and how sensitive is that to temperature. So if something that I am eating is very sensitive to temperature, let's say I eat insects, and insects are of course very, very sensitive to temperature. If the insects are moving up very fast, then I also, even if I'm not temperature stressed, even if I'm a thermal generalist, because my food resource is moving up very fast, I also need to keep pace with that. All right, I think we'll end here. Thank you very much, all of you, for joining this session. And I hope you got something out of it, and that it was not something that you all already knew. I hope that there were some new concepts, and we were able to bring you sort of what's actually the global change drivers that are influencing biodiversity, what the state of the knowledge today is in terms of the research that we're doing in understanding how biodiversity responds to global change drivers. And those of you who have signed up for meeting individual faculty at 2 p.m., please do join the Google Meet link that has been provided to you. And see you soon. All the very best with your future work, and goodbye. Best of luck.